All right, so let's do this thing. Um, okay, so we're going to do the review here for the last unit test. Covalent bonds are formed by a non-metal and a non-metal. Hopefully by now everyone has come to grips with that. Um, and you can identify an ionic versus a covalent. Ionic, metal, non-metal. Covalent is a non-metal and a non-metal. Unequal sharing of electrons because one atom is more electronegative. That is polar covalent. All right. Equal sharing of electrons because atoms are approximately equal in electronegativities. That would be nonpolar covalent or NPC. You could have put NPC or polar covalent. Diatomic elements. Go to 7 and make a 7. So at 7 we have nitrogen, N2, O2, F2, Cl2, Br2, I2, and the last guy is H2. So when I say go to 7 and make a 7, what I mean is go to 7 and make the number 7 and just don't include AT in that because AT is too big, too many shells. And then you add hydrogen in there. So go to 7 and make a 7 and add hydrogen. Okay, so now you're talking about the different types of bonds and physical properties of. This is very important. Um, a lot of the test is going to be kind of over this. But anyway, ionic compounds, they transfer electrons. Do you remember we had that? We had a Cl and we had a what do we use? Let's use an Na, and he has one valence electron, and Cl has 7, and so he just pops that right off of there and takes it for his own. And the other thing we need to know that it looks like is, well, you'll see the pictures later on in here, but what does an ionic bond look like? It's like one positive thing and one negative thing beside each other. Polar covalent, we have a sharing, an unequal sharing, so it kind of looks like a peanut, with a partial positive and a partial negative charge. And a nonpolar covalent is just an equal sharing, so it's just two atoms sharing each other, not big hero 6. Okay, so polar covalent, unequal sharing, nonpolar covalent, equal sharing, ionic transfer. Ionic compounds, high melting points. Polar covalent, I'm going to call these both low, although this is a medium low melting point. Medium melting point, I guess. States of matter. Ionics are all solid. Ionics are all solid. Everything else can be either solid, liquid, gas at room temperature. Okay, there's no such thing as an ionic solvent, so let's just mark that off. Doesn't exist. What we have is polar solvents and nonpolar solvents. If it's ionic, it dissolves in a polar solvent. So the classic example is salt. Salt dissolves in water. Water is a polar solvent. Like dissolves like. Polar covalent, polar solvent. Nonpolar covalent, nonpolar solvent. So really the sticky one is the ionic. And you just need to know that that it's kind of more related to nonpolar, or I mean to polar, than it is to nonpolar. So therefore, it needs a polar substance to dissolve it. Types of atoms, well, we can look up here. Metal, non-metal, 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 non-metal. Covalent, non-metal, non-metal. Ionic, metal, non-metal. Let's just do this. All right. So it looks like this is going to be hard to do. So compound bond type. I'm going to be flipping back and forth. Actually, no, I'm not. I know what I'm going to do. I'm going to get another set of notes. Okay. Now I'm going to put it right here so that we can look at this all at once. All right, NH3 bond type. Well, it's two nonmetals, so I know it's covalent. I just have to decide whether it's polar covalent or nonpolar covalent. Now, honestly, I should make you do a Lewis dot and figure out how this is bonded. This has 5 electrons. Each of the hydrogens has 1, so that's 8. So that's 2, 4, 6, and a lone pair. And that lone pair means that it is polar covalent. So, conductivity. Does it conduct electricity? So what you need to know about polar covalence is that they will conduct electricity, right? You need that difference in charge. You need that partial negative, partial positive, or something. There has to be a difference in charge in order for electricity to flow through. So yes, it is conductive to electricity. That could be heat or electricity, honestly. But in this case, it is electricity. Solubility in water. Water is polar. Water is polar. And so, yes, like dissolves like. Water is polar. This is polar. Solubility in oil. Absolutely not. Oil is non-polar. Lewis dot structure. Oh, I drew it. Oh, there is a location. Excellent. Okay, CO2. All right, well, let's draw it first. If you don't remember how to draw these things, that was kind of last unit, but basically you're adding up the number of electrons. Carbon has 4 valence electrons. Each oxygen has 6. That's 12, 13, 14, 15, 16. 16 electrons I have to account for. 2, 4, 6, 8, 10, 12, 14, 16. He has 2, 4, 6, 8, so he's happy. He has 2, 4, 6, 8, so he's happy. 2, 4, 6, 8, so he's happy. This is symmetrical across both directions, and there are no lone pairs on the center atom. So this is non-polar covalent. Does not conduct electricity because there's no charge differential. Solubility in H2O, absolutely not. Solubility in oil, yes. All right, KCl. We have this, and we have this, and we have something that's highly electronegative and something that's not very electronegative. So guess what it does? It pops the electron off. And this is a metal and non-metal, so I know that this is ionic. Conductivity. Well, it depends what you're talking about. Conductivity without water or in its non-molten state. So I'm going to split this up. Dry, no. Wet, yes. Or molten. That applies to molten too. Because when it's molten, it breaks down into its positive and negative ions, and they separate from each other. They're basically moving too fast to be attracted to each other, and so you can get electricity to flow through. Solubility in water, absolutely. Solubility in oil, no, not going to happen. O2, all right, let's draw O2. 2468, 2468. Everybody's happy. Is it symmetrical across two directions? Absolutely is. All diatomics are non-polar covalent because they're all non-metal, and they are symmetrical. Conductivity, no. Solubility in water, no. Solubility in oil, yes. Okay. All right, and now define electronegativity and give the periodic trend as you go across a period and down a family. It depends which way you go across a period. Left to right, it's increasing, and down, it's decreasing. Down a family, it's decreasing. So basically, the trend is where can I put it? I'm going to put it right here. The trend with the periodic table is it's up and to the right. So a difference greater than 2O, which basically means something from up here and something from out here, that would be an ionic bond. That would be a metal non-metal. Common example, NaCl. Between 2O and 0.3 is a polar covalent. And so H2O is a polar covalent, right? And then less than or equal to 0.3, that means that they're sharing. So you can do what? You can, well, first of all, it's non-polar covalent. And less than 0.3, they basically, it's going to be a diatomic or something fairly close to a diatomic. But for my example, I'm going to use a diatomic here. Okay. Ooh, I wrote all over my notes that I have to give somebody. So let's just erase that. All right. Use the data in the chart to answer the following questions. So yeah, so this looks like, again, we're just naming off properties, right? So which of the four compounds are probably ionic? Well, it's probably going to dissolve in water. It's going to conduct electricity in water. It's going to have a high conductivity in water. It's going to have a very high melting point. So 801 and 772. So which of the four compounds? I'm going to go with sodium chloride and potassium chloride. First of all, they're metal, non-metal. I mean, that's just a no-brainer. If it's a metal and a non-metal, then you know it's an ionic compound. Probably polar covalent. Okay, so if it's polar covalent, it's going to have a medium. It's going to have a medium melting point. It's going to be soluble to water, so yes. So we're going to eliminate these two. Oh, wait a minute. I eliminated the wrong ones. I'm going to eliminate these two, these ionics that I did. It is going to dissolve in water, so it's going to be sucrose here. Got a medium melting point. Low conductivity of electricity. And then which of the four is nonpolar covalent? Well, it's non-conductive. That's going to be the big key there. Nonpolar covalent. Not going to be conductive. Not going to dissolve in water. Low melting points. Dissolves in oil. I think we have it. I think it's naphthalene. All the evidence points. So really you're just looking at the information you're given. I know that this is metal, non-metal, metal, non-metal, so I know that these two are ionic. The real question is which one of these is non-polar and which one is polar. The dead giveaway is doesn't dissolve in water, dissolves in water. So this is obviously polar. This is obviously non-polar. Which compound would have a higher melting point, aluminum chloride or carbon tetrachloride? Well, this is ionic, and this is non-polar covalent, which has the lowest. Ionic has the highest. So it's just like melting points is just like strength of bonds. Ionic is the highest, which is greater than, metallic is the highest, which is greater than ionic, which is greater than polar covalent, which is greater than non-polar covalent. That applies to melting points, that applies to bond strength, all that good stuff. Okay. Did I? Hopefully I got all that on camera. I guess we'll see when I go back. I'm going to stop the video here so it's downloadable easily, and then I'm going to start up another one.